Welcome back to my this lecture that is on aspects of biochemical engineering. And last couple of lectures we tried to discuss the that microbial system for substrate utilization, product formation, cell mass formation by using different microbes, and we made a detailed analysis on the process. Now this lecture is something related to that, but little bit advancement of the chemostat process. We know that major drawback of the chemostat process is the cell mass wasting from the reactor, because we know that because when you consider any kind of continuous start tank reactor, there is the inflow of substrate, there is the outflow of product, and when since we have it is a continuous start tank reactor, we assume that whatever cells that present in the reactor that also remain in suspension, so it is also going out with the outgoing liquid. Now, if the rate of cell mass that is going out of the from the reactor is more as compared to the cell mass growing in the reactor, then what will happen is situation will come when there will be no cell present in the reactor. So this is the major drawback of the chemostat process. And we have I try to explain the situation that the every cell has the generation time, and we know that 1 by d is equal to hydraulic retention time. Now, suppose you operate a system at very high dilution rate, and one hand so that the retention time of the liquid in the reactor much less than the generation time. So before your cell multiply, you are taking out the cell from the reactor. Naturally, you will not get any cell in the reactor. So this kind of situation can be overcome by two different approaches. One is if you recycle the cell back to the whatever excess cell you are taking out from the reactor. If you recycle back the cell to the reactor, then naturally your cell mass concentration will remain constant. There will not be the situation of cell washout. And second situation is that I told you if you immobilize the cell on a solid matrix, so that you hold the cell like this and you pass your substrate like this, though there is a less possibility of cell washout. Now, this particular that lecture we try to discuss the process with CSTR with cell mass recycling, and we have taken this with respect to one particular process, what we call activated sludge process, which is largely used for wastewater treatment process, because we know that there was a survey in India that long before 15 years before by the Central Pollution Control Board, and they observed that most of the chemical and biochemical industry in India, they are contributing the wastewater pollution problem, and it is mandatory for all the industry. They should before they dispose the wastewater to the water courses, that should be treated properly, so that they should not have any kind of harmful effect on the environment. So this the activated sludge process is largely used for the wastewater treatment process. So this I am going to discuss this in the lecture, and also I am going to discuss how we can do the process design, because that we try to develop the equation. Maybe in the next lecture I shall give you more detailed information how we can do the detailing of the process design. Process design means to run the process, whatever parameters we shall have to calculate. What are the different parameters we should calculate, we should determine for running a particular process. That I shall show you in the next lecture. But this lecture will try to analyze the activated sludge process. Now, if you look at the activated sludge process, what do you mean by activated sludge process? Activated sludge process is a continuous start tank reactor with cell mass recycling. That means we know this is a continuous start tank reactor. Am I right? There is the inflow and outflow. Then with cell mass recycling, that means there will be some kind of cell separator. A part of the cell you recycle back in the system. So this is called CSTR with cell recycling, am I right? So that so activated sludge process is nothing but this is the feed and this is effluent. This is your effluent and this is sludge wasting. Okay. Now it is designed to remove the soluble biodegradable organic matter, because here let me explain that, because you see that when the wastewater contains some kind of organic matter, how we can remove. Now if we use any kind of chemical process, we shall have to use some kind of chemicals which have the oxidizing property, as for example potassium diachromate, potassium permanganate. So that that we use if you treat this wastewater with this oxidizing agent, then all the carbonaceous matter that will be converted to carbon dioxide and water. But the problem is that when you use any kind of chemicals for the oxidation of organic matter, so first of all it is energy intensive. You have to heat it at high temperature. At the same time you have to use lot of chemicals. But now when we use these chemicals, particularly heavy metal toxicity of the water, that will be increased. As for example, potassium diachromate, if you treat the wastewater, that means chromium concentration of the water will increase. The potassium permanganate, that if you use the manganese concentration in the water, that will increase. That is undesirable. So but if you look at the biological process in another way, that if there is any kind of soluble organics present in the wastewater, our bacteria can easily utilize this organic matter for the growth and multiplication. When they grow, these soluble organics can be converted to insoluble biomass, and this insoluble biomass, which is insoluble, we can easily separate it out. If you separate it out, you will find it is a clear liquid, and that is why that the activated sludge process is largely used for the wastewater treatment purpose. The recycling provides the cell mass concentration almost constant in the reactor. I told you the main purpose of recycling, we want to maintain the cell mass concentration uniform, so that rate of reaction in the reactor should remain constant. And recycling is necessary, increases the mean cell residence time. Now since in this reactor, if you do the recycling, then what will happen? The recycling, that means what I say, the cells we are recycling back, that means the cell retention time in the reactor, that will increase. That is why, that is exactly so. In that case, the mean cell residence time should be higher than hydraulic retention time. Now in case of CSTR or chemostat, what is happening? The mean cell residence time is equal to hydraulic retention time. Am I right? But as soon as you do the recycling, then the mean cell residence time is higher as compared to hydraulic retention. This is the main purpose of recycling. Now this is how this process diagrammatically I can explain. This is wastewater. First we have the preliminary treatment. Preliminary treatment, it has might be having some floating matter. It might be the bigger particles that is usually separated out by the settling process. And then we have primary clarifier, where that smaller particles, suspended particles, that will be separated out. After that is passes. This is the activated sludge process, where what we call it a aeration tank, where the aerobic organism will grow and utilize the soluble organics for their growth and metabolism. Then this cell mass is the insoluble mass that is separated by the secondary clarifier system, and then this cell mass we separated out. This is the waste activated sludge, and the clear liquid is take it out, and we use some kind of disinfection like chlorine treat, and finally we dispose to the water courses. This is how the process is operated. So basically our activated sludge process is the CSTR with cell mass recycling. This is the process that we have. Now if you look how it is in practice in the industry, it is like this, that this is the surface aerator. This is called surface aerator. The surface aerator that flowed at at the top of the liquid. Now here you can see that how the surface aerated is located in the actual activated sludge process. It is located at, so what they do, they throw the water out. You can see that it is they're throwing the water out, so that when you throw the water out, then air will come in contact with the water, and more air come in contact with the water, the dissolved oxygen concentration in the water will increases. So that if the dissolved oxygen increases, then your organism will grow more, and they can utilize more soluble organic material for their growth of the organism, and the degradation of the organic matter will be more, which is most desirable. Because in case of aerobic fermentation process, major limitation factor is the dissolved oxygen concentration, because we know the microorganism can utilize the oxygen which is dissolved in the liquid, not like human beings. We all human beings, we can take the oxygen which is present in the air, but microorganisms, they can utilize the oxygen which is dissolved in the water. And since oxygen is sparingly soluble in water, so that is the limiting factor for the growth of the aerobic organism. So we will have to increase the dissolved oxygen concentration of the in the liquid, so that our organism can grow very fast and it can utilize the substrate at the faster rate. Now that is why we put the surface aerator here, and then so this is how it looks. So question comes, what are the principles of activated sludge process? Now activated sludge process uses the microorganism to utilize the soluble organic contaminants present in the wastewater. What I just now I try to point out, the soluble organics converted to the insoluble biomass. Then common bacterial species that use in the activated sludge process is Jockleya remigera. This is the typical type of key organism that is used in the activated sludge process. The important characteristics of this organism is that it is synthesizing, or it produces secreting the polysaccharide gel. Since the organism, because we know bacteria, what is the size of bacteria? Size of bacteria varies from 0.5 to 2 microns, and they are very tiny particles and very difficult to settle down. So that is the major problem, because whenever we handle any kind of bacterial process, the major problem we face, that is the separation of the cells. And this organism has the characteristics of secreting the polysaccharide gel, and since it secreted polysaccharide gel, the cell, they will be attached with each other, and they will form the floc. They will form the floc, and this is called floc formation. And then the particle size will be big, and as the particle size is big, it will settle down. Because of this gel, the microbes agglomerate into floc, and which is called activated sludge. The special property of the activated sludge is high affinity for suspended solid, including the colloidal biomass. So that that this suspended mass, what will be some the small particles that present in the wastewater, they absorb on the surface of the cell surface, and your wastewater, you will find the clear water. Because I can tell you that my personal experience, that when I was at IIT Delhi, I visited the Okhla sewage treatment plant, and if you visit the Okhla sewage, I don't know how it is now, but I visited in the year 1983. Then I found, when I took the water in my hand, I found immediately that cell that settled down, and I get the clear water at the top. So this kind of experience that I have. Now for ASP design based on three different parameters. One is biochemical oxygen demand. Now what do you mean by biochemical oxygen demand? Biochemical oxygen demand means, as I told you, when organisms grow and multiply, they require the dissolved oxygen. Am I right? So more the organism grow, more will be dissolved oxygen consumption. So biochemical oxygen demand means the amount of oxygen required for the oxidation of the biodegradable organic matter. So this BOD is directly proportional to biodegradable organic matter. is directly proportional to the biodiversity. So, suppose if the BOD value is high, that means this has more biodegradable organic matter. If your BOD value is low, that that is a less biodegradable. In this connection, let me tell you that our drinking water, we know the drinking water, as per World Health Organization WHO, the BOD of the waste that drinking water should be less than 6 milligram per liter. Am I right? What we call 6 ppm. So this should be less than 6 ppm. Now the mixed liquor suspended solid and mixed liquor volatile suspended solid MLSS and MLVSS, that is very important. That that suspended solid, we understand the suspended solid. How you what you call sludge? How you define the sludge? Sludge is the kind of insoluble solid material. It may comprises of both inorganics and organics. Am I right? So similarly, that that when we have the mixed liquor suspended solid, it has one is suspended, another is volatile suspended solid. Now, what do you mean by volatile suspended solid? Now, if you burn it at 600 degrees centigrade, then whatever organic matter is there, that will convert it to carbon dioxide and all the oxides, sulfur dioxide, nitrogen will convert it to nitrogen oxide, metal will convert it to metal oxide. But that metal oxide that remain in the form of gas in your system, but gas will go out of the system. Gas always you can go out of the system. So whatever things is converted to the gas, that we call it volatile matter. You get my point? The volatile matter indirectly it tells the organic content of the solid material. So since our biomass or cell mass comprises of mostly the organic matter, that is why volatile mixed liquor volatile suspended solid, what we call MLVSS, this we usually consider the biomass or cell mass. This we express as biomass or cell mass, because when you burn it, it produces carbon dioxide and carbon dioxide, sulfur dioxide, nitrogen oxide, that will go out of the system. This is the organic material. And specific oxygen uptake rate, this is very important. The reason is that since it is the aerobic process, question comes that how much oxygen is required for the oxidation of the sample. So that is why this is very so these are the things. Other parameters like that suspended concentration of the cells and the outgoing liquid, that is effluent, is significant but not directly controllable. So we assume the outgoing the effluent should not contain much of cell mass, because most of the cell mass we assume that is usually separated in the clarifier. Now question comes that what do you mean by biochemical oxygen demand? Is the amount of dissolved oxygen that needed by the aerobic biological organism to break down the organic material present in a given water sample at a certain temperature over a specific period of time. Now usually we consider 5-day BOD. Now why we consider 5-day BOD? Now if you look at BOD is a biochemical oxygen demand, am I right? BOD versus T, that is like this. Now this is 5-day, and suppose this is 20-day, am I right? All the organic matter that will be oxidized. Now here 5-day we have observed that approximately 70% organic matter will be oxidized. Now since it is the operating parameter, naturally we are interested that in how this parameter can be monitored very short time. That is why we express as 5-day the BOD. Now for the purpose of that process design, the measurement of BOD-U, what we call ultimate, this is called BOD-U, and this is called BOD5. So this is impractical, because you have to wait for 20 days, that is not feasible. Now best approximation is obtained through the use of chemical oxygen demand. Because why the chemical oxygen demand is very good? Because chemical oxygen demand is the amount of oxygen that is required chemically for the oxidation of the sample, and this can be done within 2 hours. You just take the sample and reflux with potassium diachromate for 2 hours. All the organic matter, all the inorganic matter, that will be oxidized. Then you calculate, you through titration you find out how much potassium diachromate has been consumed. So from that you can find out the COD value. Now the COD of a sample, if you see here, this will keep on decreasing with respect to any treatment process. This keep on decreasing. A time will come when it is constant. Now this, when it is constant, and this is the input and this is the final value, and this difference is this is actually the BOD value. So from the COD value we can also find out, extrapolate the BOD value with the help of this particular curve. And BOD estimate by the aerated method. The dissolved oxygen concentration can be estimated by the 2 methods. One is by using the dissolved oxygen probe, another by the chemical method, what we call aerated method. We can use that. Now mixed liquor suspended solid, to achieve the high conversion of a high cell biomass concentration is required, and most commonly measured the cell. The ratio of this is not constant, but ratio plays very important role. MLVSS, I told you MLVSS indicate that how much volatile suspended solid is there. That means volatile suspended solid indicate that how much cell mass is there. Now if the ratio is more, that means your suspended solid contains more cell mass. If the ratio is less, that means suspended solid contains less amount of cell mass, that is inactive material. So that is undesirable. So typical range of MLVS by MLSS is 0.75 to 0.95 depending on the wastewater and system operating conditions. Specific oxygen uptake is defined as the rate of oxygen required both for substrate oxidation and the growth of the cells. Now specific oxygen uptake, I told you this is equal to 1 by x dO2 by dt. Am I right? This is the rate of oxygen consumption, and this is 1 by x is called the specific oxygen uptake rate. So this is, we can write that the oxygen must be transformed from the gas phase to by some mechanical means. I told you surface aerator. I told you surface aerator. I show you aerator is used to transfer the oxygen present in the air from the air to the water, and currently transfer rate is 1500 to 1700 grams of oxygen per meter square meter per day are economically used for air, the oxygen source. Now this is the activated sludge process. Let us see how you can design that. In case of activated sludge process, I told you this is the CSTR and this is the settling tank separated, and you recycle back the cells here. So it is CSTR with cell recycling. Now here 3 assumptions we made. The influent, this is influent and this is the effluent. Am I right? Influent and effluent concentration is negligible. H0 becoming S, this H0 becoming S as soon as this fold in the reactor due to the complete mixedism, and all reaction occurred only in the bioreactor, not in the pipeline or separator. Now if you have this, then we can write at the steady state condition biomass balance is the what is X, Q0 is the flow rate, Q0 in the X0 is the input cell mass, then what is the biomass growth, what is generation is the, we can write this is the growth of the cell, this is the death of the cells into V, this is the volume we have to consider. And biomass output, what is the output of the biomass? That output is going out here, because we want to do the balance across this system, not across the reactor. So there is a 2 outlet, this is QO0 into XC, and this is the XW is the wasting flow rate, and XU is the settled cell mass concentration. Here is the XC. Now assuming because in this problem we have made certain assumption that influent and effluent and effluent concentration of cell mass is negligible. Am I right? So if we assume that influent and effluent cell mass is negligible, then we can write this equation in this form. This is V equal to this is equal to K, and this equation I can write in this form. That is mu max S by K S plus S equal to QW XU by V into X plus mu D. And then if you do the substrate balance in the similar way, Q into S0 is the rate of substrate that input, and substrate consumed is this one, and substrate what is the output? One is with the effluent, that is Q0 into S and QW into S. So, and this is if you do it, this will be Q0 into S, and if you simplify, you will get this particular relationship. Now, if we consider both the equation 2 and 3, then we will get this equation. We will get this equation that QW equal to QW into XU Bx mu D equal to this. Now here, as I told you, the main purpose of recycling is to increase the cell residence time. Now in the reactor, what is the cell present in the reactor? This is the volume of the reactor and X is the cell. The total amount of cell is total amount of cell is how much? Is V into X, am I right? And what is the cell wasting from the system? We assume most of the cell is going out from the recycle tank, and this is coming in. So this is what QW and XU. That this here we have QE into XE, but this we assume to be 0. Am I right? So we assume most of the cell that is wasting from the this wasting line. So what we can write, that mean cell residence time is equal to what? Equal to Vx divided by rate of that the cell that is wasting from the system. So this will the unit will be time. So this is exactly what we have written here. You can see this is written here like this, and if we put this value, and this is equal to theta c. Now we can put this theta c here, 1 by theta c, and then finally we will come across this equation x equal to this equation, and this equation we can write. We know theta. What is theta? Theta is the hydraulic detention time, V by F. Am I right? So we can easily find out the volume of the reactor. So we can V equal to, from this equation we can find out this relation. So we can easily find out the volume of the reactor. Now for the computational model, the ASP is similar to the microbial process, and the Monod equation we use for the, and Monod equation, this is the modified Monod equation. Monod equation is this one, mu equal to mu max S K S plus S, but we modify because cell death is occurred in a particular in a living population. So the net growth of cell equal to growth of the cell minus the death of the cells. The BOD removal rate we can write Qs equal to Q max S by Ks plus S. This is without considering the endogenous metabolism of the cells. Now these are the different constant value that is shown here. This we quoted from this reference. So these are the different range is like this, and typical values are given here. Now here we have come across a new term, what we call F by M ratio. What is F by F? F stands for food and M stands for microorganism. Now how you can find out what is the food? The F into X. F is the volumetric flow rate, S is the substrate concentration, and what is the microbes present in the V into X? So this is called food by microorganism ratio. This how the unit is time inverse. This is used to designing the loading of the ASP. The FM ratio usually reported at BOD per gram of ml/VSS per day. So this is the another very important problem of the activated sludge process. I told you the separator where the cell mass is separated. That is the sludge volume index is a kind of important parameter that determine the settling characteristics of the sludge. Now here we can find out that sludge volume index is the volume occupied 1 gram of activated sludge of the mixed liquor solid after settling 30 minutes in 1000 milliliter graduated cylinder. Now, if the sludge volume index 35 to 150, then it is a good settling sludge. If it is more than 200, it is called bad sludge. And healthy sludge contains significant population of filamentous organism and protozoa present are mainly stalk ciliated species. The poor sludge contains filamentous bacteria and fragilated protozoa. So these are the problems. So the sludge characteristics also plays very important role. Now this is the how the clarifier looks. This is, you can see there is here the sludge that will settle down at the bottom, and this is little bit inclined, and this is a scraper, and this scraper it rotates very low speed and scrap in that way in a manner so that all the sludge will come here, and then we can take this out from this in this direction. So and that the solid that clear liquid is usually comes out from the top. This is how the clarifier looks. Now, sedimentary tanks design of sedimentation tank is based on two factors: overflow rate and solid loading rate. Overflow rate defined as the flow rate divided by the surface area is equal to the critical settling velocity under the ideal condition. Values are in the range of 200 to 500 cubic meter per square meter per day range, and solid loading is 3 to 6 kg per square meter per hour hour range, and the depth of the horizontal velocity is 30 meter per hour, and the hydraulic detention time is 2 hours to provide 1 meter sludge storage. The typical depth is 3.5 to 5 meters. So in this particular presentation, I try to discuss that what do you mean by activated sludge process. I told you that activated sludge process is a process through which you can remove the soluble organics present in the wastewater, and also it is a process through which the drawback, one of the major drawback of the chemostat process, that is the cell mass wasting from the reactor, is can be, or that what problem that we face, that is cell washout, that problem can be overcome. So how to analyze this system, that I try to explain, and also I try to find out that mathematical correlation, just to find out how you can determine the cell mass concentration in the activated sludge process, how you can find out the volume of the activated sludge process. And I told you, whenever you do the recycling of the cell, main purpose is to increase the retention time of the cell. So in this case, the solid retention time or mean cell residence time will be more than the hydraulic retention time. And also I try to discuss that the settling characteristics of the sludge. I told you, if the values lies in between 550 to 150, then it is a good settling sludge. Is more than 200 is a bad sludge. So and how the clarifier looks. So this I try to explain here. I hope in the next lecture I try to discuss the process design of the activated sludge process. Thank you.